So at the very beginning last week, when we talk about clustering, what constitutes a cluster? Distance, central based, contingency based, and we also look at density. So sometimes you would have data points that have different density, and you want to cluster those dense areas as one cluster, and maybe the surrounding scattered area as outliers. And density-based clustering methods achieves that. So we need to, for density-based clustering methods, we need a whole set of different terminologies. So we're going to introduce those. So first of all, density is the number of points within a specific radius. We call it epsilon. So density-based clustering methods, they can all discover clusters of arbitrary shape. The clustering is guided by the density. If this dense area has a irregular weird shape, they will all be recovered. All density-based clustering methods can handle noise and helps identify outliers. And the density-based clustering algorithm can be achieved using one scan of the data set. The only thing for density-based clustering methods that's probably not good is there you need to set some parameters. And for certain algorithms, they are very sensitive to the choice of the parameters, the values that you set. So interesting studies, I think we will cover all of those actually, because they all are very interesting. They all have unique contributions. So we're going to look at DBSCAN first. DBSCAN won the 2014 Test of Time Award from the KDD, Knowledge Discovery from Database. So and DBSCAN established a set of vocabularies that's being used for other density-based clustering methods. So we're going to actually go through those. Earlier we defined density, and now we're going to look at other things. So points in observations. So points here are observations. In a density-based clustering algorithm, they are categorized as three groups. Excuse me. They are core points. Core points is the points that within the radius that we specified, 1 cm, they are a minimum of 5 points. So those are the core point. So this is the core point. Within the radius, there's 1, 2, 3, 4, 5. And we can see this is probably also a radius within a core point within the 1 centimeter radius. It has at least 5 points. Border points are the points that within the neighbor of a core point, but itself is not a core. This point is within the neighbor of this point, but itself, if we move this, if we move this circle surrounding this one, you will see its radius does not have 3 minimum points. Therefore, that's a border point, not a core point. I think this is good. Then outliers are the points that's not even within the neighborhood. It's completely outside. Okay, so the density-based clustering needs 2 parameters, epsilon and minimum points. That defines how dense, what dense means for this clustering algorithm. So epsilon again is the radius, minimum point is the minimum number of points in this neighborhood. I think we have described all that on core and border and noise. Do we have questions on those?
I have a question.
Yes.
How do you select the core points?
you pick a point and draw and count how many data points is less than epsilon distance away from it, and see if that number actually exceeds the minimum points.
Okay.
Yeah, so we can operate based off a similarity matrix.
Okay, so if we pick the core point A, for example, then I see that there are at least a minimum number of points within the distance. Then find the next core point. I remove the points that I have already.
No. This is a clustering algorithm. We try to find dense areas. We try to see core point. We're going to talk the detail about the algorithm. The core point is, the key idea is that the core point resides in the center of a group of points that make this a attractor. We see all the other points within this cluster, within this radius, should be attracted to the same cluster as A resides.
Yes.
Right? Yeah.
Right.
And we move away to see if the border points within A may be also a core point. If we move this core point and its surrounding area, then this surrounding area should also be drawn to the same cluster as the original core points. So you can think of a core point as like magnets. It's attracting points that belong to its cluster.
Okay, my question is, in previous plot, point A is a core point.
Yes.
What if I select a point that is very close to it, one of the points that are very close to it? That can be a core point as well, right?
Yes, exactly. Yeah. Sorry, your question did not came through.
So my question is, now point A is selected as a core point, right? A point that is very close to it. For example, the one that is below point A. That one can also be selected as a core point.
It can.
It can, right?
It can, yeah. As long as it has this number of points around it.
So I might have like a lot of core points in this.
Yes, the core points will be easily just to put into this cluster. We're going to get to there. You're ahead of the rest of us.
Another question here.
Yeah.
Does the core point itself count to the min points?
Yes, it does.
Okay.
Yeah. Sure. Okay, so we need to actually get a few more definitions before we move on to the algorithm itself. Well, those terminology, I think it's important because if you read any density-based clustering algorithm papers, you're going to run into those. So you need to become familiar with those terminology so that you can actually explore on your own in the future on density-based clustering. Directly density reachable, meaning, okay, the definition is here. A point P is directly density reachable from a point Q with respect to our definition of epsilon and minimum points if Q is a core point and P is within the neighborhood of Q. What it says is directly reachable. So if anything is directly reachable from some point, that some point has to be a core. And this point has to be within the neighborhood of that core. So basically, what you see here, if I have a core point Q, I draw that radius. Anything within my immediate neighbor are directly reachable from me. Does that make sense? I think it should. So all the points in my, so I'm Q, in my immediate neighbor, the epsilon, are directly reachable from me. I'm going to see how far I can reach. There's something that I can be indirectly reachable from me, but anything, as you can see, can directly reachable from me should belong to my cluster. So you can keep that idea in your mind.
So
So
is it just, sorry, is it just saying that it's in my neighborhood, but I don't want to just use that criteria. I also want to use a criteria that it's in a neighborhood of a point that is useful in some way, like being core.
Yeah. This is the first concept because other concepts going to be built on top of it. When we talked about directly density reachable, and next we're going to talk about density reachable. So this is not direct anymore. I can reach this. So P is reachable from Q if Q is a core point, and there are some intermediate core points that connects P to Q. So there has to be some intermediate core points that P is reachable from. And then through several jumps that Q becomes density reachable from, P becomes density reachable from Q. So P is not directly density reachable because it's not within the neighborhood of Q. But it is within the neighborhood of some other points, which is a core point and also within the neighborhood of Q. So this chain can go as long as there is enough of a dense area to support those core points. But the idea is my path from P to Q is all dense. There's lots of data points concentrated on my path. Therefore, P is density reachable from Q. Therefore, in clustering, P should belongs to the cluster that's including Q.
So do we always start with the core point and then so all these definitions are with respect to core point? Okay.
Correct. Yes. So Q has to be a core point. And along this path, only P may be a non-core point. All the other points should be core points. So reachability is not as symmetric as Saba just mentioned. It's not a symmetric relation. Only no point may be reachable from a non-core point. A non-core point may be reachable, but nothing can be reached from it. If you see reached from, then this it has to be a core point. So basically the idea is only the core point can attract points to the current cluster. Border points cannot attract additional points to this cluster because it's already on the border. If you attract, you're going to attract a noise to this cluster.
I have a question. Can you go back, please?
Yes.
Does a non-core point may be reachable, so it makes sense, but nothing can be reached from it.
Yes. It has to be a core point for something to be reached from it.
Oh, it's just a definition. Okay.
Yes, it's just definition. Yeah. So then density connected is a symmetric relation. As if these 2 points, so this 2 point may be border points, but if there is a core point that's density reachable, that they are density reachable from, then these 2 points are density connected. Meaning there's the distance in between of P and Q are occupied with dense points. That's a more intuitive way to understand this. So density connectedness is a symmetric relation. If P is density connected to Q, then Q is density connected to P. They don't have to be. They can be core points, but they don't have to. Okay, so the clustering. So now after we define all those concepts, and we can talk about clustering. What is a cluster in the context of density clustering? So a cluster indeed, with respect to our parameters, satisfy the following two conditions. One is basically says all points should belong to the cluster are in the cluster. So what does it say? It says for any P and Q, if P is in the cluster and Q is density reachable, so P is in the cluster already. If Q is density reachable from P, then P is a core point. If P is a core point and Q is density reachable from P, then this Q must be also in the cluster. This is exactly what we have mentioned before. Basically, any points that can be attracted by core points should be attracted to the cluster. Second condition is basically says all points in the cluster are density connected. There shouldn't be any noises, outliers in this. So for anything that's inside C, so anything that belongs to the cluster, then they must be density connected. Okay, I think those are fairly intuitive. It's just, you know, when you expressed using those mathematical symbols and, you know, using those new terminologies, it reads like very strange. But the idea is very clear. It's basically saying that core points attracts points, and this attraction can be passed through multiple different core points within the same path, and anything that's included in this cluster must be density reachable, density connected. So we don't want noise in this. I like this animation, so I must show this to you. I think this is going to answer, at least visually show you how this works. So we can choose whatever let's try this pimpled smiley. So we have defined epsilon. I don't remember what those pink points and empty points. I thought we only have those, but let's start. We have the epsilon set to be 1 and the minimum point set to be 4. So if we, what? Go. So we start with 1, and then we trace the reachable points, because there's in between core points in between, it can still reach a lot of border points and other core points. Other core points going to attract more of its neighbor points into this cluster. When this cluster can no longer be traced, then the system is going to pick another random points. To grow the cluster. So it tested lots of little things, but none of those meets our mini points of 4. So those end up to be outliers. Okay, you can play more of it. I just love those animations. I think they make things much easier to understand. Arbitrary points and attributes, I think it's all, what is right here is all inside this demonstration. So earlier we said we have these two parameters we need to set. One is epsilon, one is minimum points. So minimum points is, it doesn't have to be large. As you can see, it only defines how tight every clusters need to be. So there is a heuristic way to set this min points greater or equals to the number of dimensions in the dataset plus 1. Once we have the min points set, then we can use this graph to decide what's going to be our epsilon. Epsilon again is the radius. So we need to find the largest radius that hold 4 nearest neighbors, but which epsilon we should take. So we will graph this. So for points in the idea why this graph works is because intuitively we know that if the points are in a cluster, then their fourth neighbor, the distance from this point to their fourth nearest neighbor should roughly at the same distance. Noise points, however, are going to have a much larger distance to its fourth nearest neighbor. So we can sort all the points. So those are our 3,000 points. We sort those by the distance of this point to its fourth nearest neighbor. This is going to give us a curve like this. And we will pick this knee or bending point. That's the place that we can separate clusters from outliers. So in this case, we can set epsilon to be 8, maybe. So this is the way to set epsilon.
Does that mean if we set k, sorry, not k, we set the min points,
yeah,
then the epsilon can be determined by the system, or it's a visual?
It's a visual. You have to decide it. The system doesn't decide it for you, because for DBSCAN, epsilon is actually very sensitive. 8 and 8.5 could give you a very different result. So you have to try. And that's why we need to talk about obstacles. It gives you an alternative way to looking at epsilon. But for now, just keep in your mind, epsilon is a very sensitive thing to set for DBSCAN. Input order. For the core points are always going to be, no matter the input order of your data set. Remember, we start with a random point and we read through. We scan its nearest neighbor and go to other points in its nearest neighbor and expand its nearest neighbor, and we grow cluster that way. The input order does not affect core points. No matter where you start, core points going to always be grouped in the same cluster. But order points may be grouped into different clusters depending on the order of the input. This is intuitive, and I personally don't think this is a huge problem. So when DBSCAN works well, it does perfect job of finding those dense areas and exclude all those outliers or noises. So resistant to noise can handle different sizes and shapes, but it could actually be very sensitive to, as we said, epsilon. See, this is 9.7275, this is 9.92, and you get different result. So it doesn't work very well when you have a very varying densities that on top of that you have your epsilon not being set very well. You could actually find the perfect epsilon that actually gave you exactly the output of the original input. But when you pick the wrong epsilon, I mean just a slightly different epsilon, you'll get very different things. So there's more pictures to show how sensitive this is. The epsilon 0.4, 0.5 give you different results. That's why optics is invented.